Hey guys, and welcome to goBILDA TV. My name is Ethan, and today we're going to be talking a lot about servos. Servos are a fun topic, something that can be really complex or really simple, just depending on how you look at it. We're going to go into different kinds of servos, what differentiates gear trains from other gear trains, motor types, case material, and a bunch of other really fun stuff like that. Make sure if you have any questions to tag us at goBILDA TV in the chat, and we'll kind of dive in. So the kind of baseline, the biggest thing is, what is a servo? A servo is a motion device that's generally designed to rotate about 180 degrees. It will be a closed loop device where you're sending it to a specific position, and it will run to that position and pretty much stop when it gets there, and then do its best to hold its position. So most of the time they are a closed loop position device. Sometimes they can be a closed loop velocity device where you ask your servo to go a specific speed, and it will go that speed and do its best to stay there. And that's another very valid kind of closed loop device, but generally something like a continuous rotation servo will not be a closed, or continuous rotation servo will not be a closed loop velocity device. It'll likely still be open loop. So most of the time your servo, if it's going to be a closed loop system, will be a closed loop position system. As far as goBILDA servos go, we have 3 different ratios of our 2000 series servos, the torque, speed, and super speed servos, and they're really designed for kind of 3 primarily different applications, where you've got something that needs to be really fast, somewhere around 275 RPM. You reach for a super speed. A speed is that really nice middle ground where you might want to run a linkage or run something that is lever arm based. And the last option is the torque servo, where you just need the amount of torque to lift up something or move something that requires a lot more force, but doesn't have to happen in any necessarily fast amount of time. These 3 servos will all have the same amount of output power. So that draws on the really necessary distinction between power, speed, and torque. So speed and torque are both independent things, and they can come together to create power. Power is the amount of load or the amount of work done over a specific amount of time. So while this can have 275 RPM and this torque servo can have 50 RPM, they can still put out the same amount of power, or a very similar amount of power. Within any servo line, you may experience some differences from servo to servo. 2 super speed servos right here might vary in output power of 5% or more, and that can be fairly normal. Depending on the direction you're running your servo in, that can change the speed and torque you get out of it, and also just exactly when it was made and other information like that. So these are all steel gear servos. Gear material is always an important thing to keep in mind when deciding what servo to go with. Sometimes you want and need something like a steel gear servo. Sometimes you may need a titanium gear servo, something that's going to take a lot of beating. And sometimes you just need something that's going to be plastic or brass. Plastic has a really great advantage if you're using a nice quality plastic. It can run for a really, really long time, compared to something like a steel gear may not run for quite as long without just wearing out. But that titanium or steel gear servo will be a lot better at taking shock loads and overall loads from a servo in general day-to-day use. So generally the hierarchy of kind of durability goes from plastic to a metal gear. Metal gear servos generally means it's going to be brass or aluminum. And then once you get into a nicer quality metal, you start saying, hey, this is the exact metal this is made of. So your aluminum servo gear might say your aluminum gear servo might say metal gear, where your steel gear servo will probably say steel gear. Let's see here. Andrea mentions breaking one. Yeah, I think a lot of people in FTC have experienced broken plastic gear servos. It's definitely something that happens a lot, and that's a big reason why the goBILDA servo line is all steel gear, because they are really kind of durable and meant for that environment, especially with the amount of power that they put out. The powertrain of a servo all comes down to the motor inside of it. So they all have this really small motor in there. It is a, let's see here, probably a 20 millimeter diameter, and it is fairly low output power compared to something like a Yellow Jacket, but it, for the size, can generally pack a pretty good punch. And the size of motor you have in your servo will depend on the size of your servo. You have standard size servos, which are kind of the de facto. Most of the time, if you're using a servo, it's going to be a standard size. You also have quarter scale servos, which are generally going to be used in an RC car that's 1/4 scale, somewhere around there. And those are can have a larger motor, which means they can have a higher output power. It doesn't mean they always do. If you compared this, even this 805, which is a really big servo, to this 9380 high-tech servo, this 9380 is way smaller. It is tiny compared to this 805. It will still put out way more power and be more efficient and generally kick the pants off the 805, but it's 3 times as much. So a lot of times those higher quality components can cost more, means you can get more out of your servo, but that kind of price to performance difference is something to always keep in mind when you're looking at buying the right servo for you. Let's see here. When you're talking about servo specs, a good thing to keep in mind is that cross-shopping between brands doesn't always get you the result you're looking for. Different brands have different ways of testing their servos. They have different dynamometers, and that can all mean that comparing one brand of servo to another may not make it a one-to-one comparison. A good example that I found personally is that a lot of times high-tech servos will pull more power than they're spec'd for, and a lot of times a Savox servo is going to pull right on what it's spec'd for. So you may look at your Savox servo and say, man, that is crazy, it's really, really awesome, compared to this high-tech servo, but in reality, there's a world where that high-tech servo pulls more even than it is spec'd for. There are also some servo manufacturers that we've found don't put out as much power as they're spec'd for, and are generally underperform the spec. So that's always something to keep in mind too. We do all our own testing and verify the results of any spec we put out there on a lot of different servos, and we've done a lot of testing on ours to make sure that our numbers are really precise and very indicative of what you can get out of your average servo. You may test 5 servos and have one be super hot and one not be quite as hot. So our specs are really designed around making it so you know you can get the spec output power out of any of those servos. Let's see here. Yellow Jacket servo when, that would be really cool. And you can make something pretty similar. You can make a closed loop system with a motor controller that can take an encoder input, or a lot of other options. So actually, if we can switch over to our secondary camera, we can see kind of exactly what makes up a servo. So this is the electronic components side of a servo. It comes with this little tiny motor here. It's wired to an ESC, or electronic speed controller, and that is what will divvy up the power to the motor and decide how much power to send it at any given time, depending on the input from the potentiometer. So a potentiometer is an analog feedback device, and depending on how it is rotated within its stroke, it will vary the amount of voltage that's coming out of the potentiometer. Basically, you'll feed it 5 volts, say, and it'll have a ground wire as a reference. And the third wire will put back out a voltage depending on where the potentiometer is in its rotation. So depending on where that wire position is, it may read 3.5 or it may read 2.4 volts. And the controller right here can read that input and rotate the motor to get to a specific position. And that's where you find the difference between a digital and an analog servo. Analog servos are much more analog. They rely on the position of the potentiometer to determine how much power to send the motor. And it's a very direct connection between those two things. So if your motor is 1 degree off center, an analog servo will only ever send it the same amount of power. But a digital servo running a PID loop and a much more modern system can use its eye function and have that tuned really well to gradually increase the power if you're stuck at that 1 degree away position. Generally, digital servos can put out a ton more power. If you look at a high-tech HS485 and then you look at a high-tech D485, your D485 is going to put out a lot more power even though it is the same motor. It just has a digital system, which means it can put out a lot more torque. It'll also draw more power, but that's kind of the give and take with a higher input, higher output system. So this motor controller and feedback loop system is pretty similar to something you can make with a robocop motor controller, for example, or a rev hub. And you can make a similar system to this using a yellow jacket motor for sure if you need something like that. But this is kind of the internals of what makes up a servo. On the end of this motor right here, you've got a pressed on pinion gear. And a question I get a lot is if you can change the ratio of a goBILDA servo by just changing the gear set. And because the pinion gear on these motor changes depending on what ratio you have, that's not something you can do. One thing that I am excited to show you guys today is exactly how you would go about replacing a gear set and how you would go about replacing a case on a goBILDA servo. So to replace the gear set, you really only need a small Phillips head screwdriver, and it's really not all that complicated. You've got 4 screws on the back of the case. You can see them right here, and you can just thread those out. I generally, whenever I'm working with screws like this, like to go across, but you should be able to thread those out, and those are the things that's holding the whole servo together. I've got the last one right here. This is a torque servo. The case does not actually change between any of the 3 servos. The case, and all of the case parts are interchangeable. The biggest thing that's not interchangeable, of course, is the gears and the motor. And the control board would also not be interchangeable because it is programmed for the exact specifications of the ratio that it's running on. You could switch it, but the PID tune would be incorrect. So you would likely end up with not very great performance. So here I've got the case off this servo, and you can see internally you've got 4 different gear stages. This goes from about 20,000 RPM off the bare motor and reduces it at each stage. So let's say you have an application where that one of those servo gears is stripped. You can remove all of these gears if you bought a replacement gear set and pretty much just set them aside. You should have 4 pieces there. And one thing to keep an eye on is you should have 2 different servo shafts. Those are these little 1/8" pins that run in bushings and that your gears spin on. So there's one right here. This supports the center stage, and there's one for the first stage that you can see right there, right directly above where the motor is mounted. If you just need to replace the gear set, you can pop your gears in. I always look for the flattest, skinniest one. That is the first one that goes on. It goes on the center right here. Let's see here. There we go. And a lot of times you can install that with the pin still in place in the bushing of the case of the servo. You may need to remove that and kind of move this gear in like so. Then you have this castle gear, as we call it, kind of colloquial, anyway, as we call it here. It goes over the second pin and those two gears should mesh. So at this point, you should be able to spin your bare motor. You should hear it wind up while you are spinning. Then you're ready for the third gear. That is this one right here. It is the second to largest gear. And you'll notice as you increase in size, the teeth size of each gear will also increase. The next gear you want to add on is the output. So this is the gear with a 25 tooth spline on it. It has a bearing pressed into the bottom, and that bearing will rest on the plastic recess in that case and just snap in. Then you're ready for the last gear. Generally, I like to install that with the servo shaft, and you may do some wiggling to get all of those gears to mesh together, because you're trying to mesh a gear on the left with a gear on the right. It doesn't always work out perfectly first time, but you should be able to press it into place. Yeah, let's see here. Perfect, okay. And that's what your assembled gear train should look like. It has 4 gears. I think there are 5 reductions total in the system. And this is about a, let's see, 300 to 1 reduction. A super speed servo has about a 60 to 1 reduction. So a lot less aggressive of a reduction. Let's say you are in a situation where your entire case is broken or has some defect. In that case, you can get the replacement gear set, or the replacement case set, excuse me. And that can be a really logical next thing to replace. So in that case, you'll actually remove all those gears. If you had a case that was cracked, you wouldn't have ever reinstalled these in the first place. But let's get those out of the way. And you'll have 3 more screws you'll want to remove. The first is these 2 screws right here, which hold the motor to the case. You should be able to back those out, and they are pretty small, so you want to make sure you don't strip them out. And once those are out, they're fairly short. You want to put them aside and make sure you keep track of where they are. Then you should be able to pull the motor out. Let's see here. It can be kind of tricky, especially if your hands have grease on them from the servo gear train that we just installed. But another thing that can be helpful is having a little flathead screwdriver to get on top of the pinion gear and press it out. But once you get those 2 screws out, the motor should come out fairly easily. This center case is a pretty rare thing to replace, but you totally can. So you'll want to remove this motor, and then inside of the case in there, there's 1 screw right here, which is holding the potentiometer in place. You'll want to remove that screw and pull the potentiometer and the motor out, and then you will be good to install those into the new case that you got with your replacement case. Now, 99% of the time, the center case on a goBILDA servo is not going to break. There really aren't very many applications where it would. The top case is the one that would break more often, whether that's from, say, maybe not using washers on your servo ears and breaking a servo ear off, or an incredible amount of shock load on that system breaking the top case. That is the most common one you want to replace. And that's always also the easiest one to replace. You don't even have to mess with your gear train at all in order to replace the top case of a goBILDA servo. You just got to remove the last top case and insert the next one on. So we'll tighten down those screws, get the motor back into place, and we will reassemble the gear train quick. One thing to note is that the pins that hold the servo gears in place are 2 different lengths. There's a shorter one and a longer one. The longer one is the center pin. The shorter one goes on the outside. And another thing, when you're putting this output spline on, you want to make sure that it's interfaced properly with the potentiometer. The potentiometer actually meshes with this final output gear to get your position. It's not based on the motor's position at all. It's all about the final output shaft. Let's see, so we're back in this position. We'll take our new replacement case, and you may notice that in our first case, the bearing is still in that. It's definitely a press. So we've got to get that out. We will use, let's see here, we've got to get that out. So we'll just use a screwdriver, get in there, and kind of give that some leverage to get it out. You've got that bearing out of there. And now you can slot it on your output gear. Occasionally this will come out with the output gear. It may not always stay inside of the case, but in this case it did. And then you can just slide your new replacement case on. It should fit really snugly with the middle section. There should be not very much gap at all, if there's any. So you want to make sure, if you do have a gap, that your gears are all are all in place properly. Let's see here. Glitches asked if we could, technically, couldn't we make our own custom case? Yeah, I think Kevin nailed this one. I don't believe that would be FTC legal. Generally, they're pretty strict on modifying servos. Even a full company like Servo City in the past has been ruled not legally allowed to modify the servos. So if you were looking at, say, a servo gearbox from them, you likely wouldn't be able to use that with an FTC if the servo itself has been modified. So an SG20 actually uses a goBILDA servo as the base, and that would not be legal. Let's see. Lance Larson asked if there's any reason we would want to open and adjust the potentiometer. I don't know of any time you would want to. And in fact, it really doesn't allow any adjustment. The output gear right here is actually splined to a little slice out of it. That interferes with that interfaces with the potentiometer. So there's only 2 alignments you can get out of the servo output spline. The servo output does have 25 teeth, so you get a fairly good amount of indexability by rotating the servo spline on that 25 tooth port. Let's see here. So we can move it, I suppose, 1/25 of a rotation. And that's going to be generally enough adjustment for most applications. Let's see here. Glitches says, I think it would be legal considering it would be still powered off the PWM port. Yeah, I mean, we're definitely not going to be experts, so for sure check the game manual and maybe post on the forum if that's what you think you'd want to do. Another fun thing that you can always take a look at is a retention clip, just like this one. This is great for if you're working with extensions and you want to make sure your servo does not ever get unplugged from the extension. That can definitely happen every once in a while, and it's really not optimal. So that works by, if you have one of these extensions with the plastic clip case right here, you'll want to make sure you align your signal wire on your servo and your extension. In this case, it's a yellow wire to a white wire. Then, making sure those are plugged in all the way, you can install this clip and just rotate them into place. These are fairly inexpensive, and they're a great way to increase the reliability of your system, and they make everything just a whole lot nicer. Stealth Biplane says, when putting a servo back together, it seems like the case screw tightness is key. Too tight and the servo won't turn. It likely shouldn't be that way. I would definitely take a look at everything and make sure, at least with a goBILDA servo, you should be able to tighten those screws down pretty tight, and they should not bind up, depending on how tight you are tightening them, of course. That's what this looks like when properly installed, and you can tug on these wires all you want, and they won't come apart. Let's see here. So that's a lot of the internals of the servo. It really is not super difficult. There is a motor, a gear train, a potentiometer, and a controller. Let's see here. Yeah, I guess if you change the servo case, it probably would be an illegal. you would be modifying the internals of the servo. If I was your robot inspector, I probably wouldn't let you pass. But you definitely would want to ask on the forum and have someone back you up if you are intending to go to a competition with a 3D printed servo. Even if you used all the same internals from a goBILDA servo, I think that would be pretty risky business. Stealth Biplane asks, should we put white lithium grease or something similar on the gears when rebuilding? Definitely, that's a great idea to make sure those gears all keep running really smoothly, and to definitely keep efficiency up and keep the friction in that system pretty low. So our goBILDA servos are all brushed servos. So that means the motor internally will be a standard brushed DC motor. And that is really great. It's very affordable and you can get some pretty good power output, but it's not the only option. The two other big options are cordless and brushless motors. Cordless motors are really similar to brushed motors. They are brushed motors. Cordless is a kind of subset of brushed motors, where you have a different internal design that can reduce the weight of the spinning components in the servo, and that can increase efficiency and make it so you can respond to different circumstances more quickly. Same reason a titanium gear set can be a big advantage in a servo. You get a lot of the strength out of that gear set like you would out of a steel gear system, but your gear train is lighter, which means all that rotating mass that can sometimes be moving at 20,000 RPM can be cut down, and the inertia of that gear train can be reduced significantly, which is really nice. Cordless motors operate on that principle, where reducing the rotating mass can really help with increasing efficiency. And generally, most of the time, your cordless servos are going to be kind of that mid-range, or they're not crazy expensive, but they're also not very affordable for most teams. A good example is the D9 series of high-tech servos, and most cordless servos I've interacted with have also had a pretty loud whine. Savox servos do this as well as high-tech ones, so it's pretty easy to tell that you have one of those. Let's see. So the third option is going to be a brushless motor. A brushless motor is going to be the most efficient, best, highest output power generally option for you. It'll be the most expensive, but if you need a servo that is pretty much going to act like a motor, that's where brushless can be really nice. Brushless can also mean really, really low chance of burning up. Where brushed and coreless motors really have a hard time is when you're running a ton of power through one specific position, where you're running one set of commutators through and one set of brushes, and that specific set can burn out. Generally, this will look like a dead spot in your servo, where it might wobble back and forth between a specific position that you set it to. If you're having it hold an arm in place for a long period of time and you add a ton of load on that arm, that is really not a great situation for servos. Mr. Cool asked if we can ride the trike in the background. I don't think I have the batteries charged right now, but sometime we definitely should and put a video up. Lance Larson asks, when wiring the servos, do you recommend always adding the servo power module, or is that generally not needed? So the servo power module does two things. Firstly, it lets you run your servos on 6 volts because it has an independent step down from the voltage regulator in the expansion hub. It can run at a higher voltage, which means you'll get more power. Your motors and your servos will run faster, and they'll generally generate more torque and draw more current. The other facet of the servo power module is that it lets you draw more current. An expansion hub, each pair of 2 ports, say 0 and 1, are both going to let you pull about 2.5 amps, 2 or 2.5 amps, I can't remember exactly. And that's a lot for most servos. But if you're looking at a D950, this servo will pull 7 amps, I think, at stall. It won't do that for very long, but it will. And that will mean if you pull more than that threshold of 2 or 2.5 amps off of that 5-volt line on the expansion hub or the control hub, you'll brown that system out and it'll disconnect. So I've actually seen some teams running really high power servos directly off an expansion hub and having events that look kind of like electrostatic discharge events, that are just their servos drawing too much power and their expansion hubs momentarily losing connection and then coming back and sometimes being able to reconnect. If you've ever heard of the story of Ford Field in RR1, where Gluten-Free frantically tried to add a servo power module to Landgro's robot, that's a big reason, because it can increase reliability of not just the servo, doesn't just increase the power of your servo. If you're running something that's going to be a really high power, you can run into issues by running it directly off of the expansion hub. The other facet is that that's not legal. You couldn't legally run a D950 directly off an expansion hub because it would be rated to pull more power than the expansion hub could put out. Same thing if you ran a servo that was only spec'd to run off 6 volts. You couldn't run that legally off the expansion hub. That's a pretty specific rule for your general robot inspector to know, so that doesn't always get caught. That's a big reason Jack was able to play up until Ford Field with a servo that would technically be illegal, because knowing all that servo current draw specs off the top of your head is a lot to ask of a volunteer. So that's a big thing to keep in mind. Not only can it give you more power, it can increase your reliability. I would say if you have a servo in a low load situation where speed isn't very important, running it off the rev hub is perfectly fine. And it can be a simpler system. You don't have to run your extension from your expansion hub to the servo power module and all of that stuff. And goBILDA servos are spec'd to run pretty close to that limit of 2 amps on the expansion hub. So they're perfectly fine running 5 volts right off the hub. That's a big reason we chose the amount of power output that we did for the goBILDA servos, is that they are right as hot as we can make them while still not having any big issues with that system. So, coreless and brushless motors. Coreless and brushless are both generally going to be higher output power and generally going to pull more power. But with each step up, you're going to get more efficient. So, a brushed servo, if you gave it the same amount of power as a cordless servo, the cordless servo is probably going to put out more power. It's going to be a more efficient system. Same thing with the brushless servo. The brushless servo is going to put out more of the input power than a cordless or a brushed motor. And along with not burning out and being generally really robust, that makes them the really top of the line systems. But you're going to have a really hard time spending less than $100 on a brushless servo. And you're going to have a tough time spending less than 50 or 60 on a cordless servo most of the time. So as you increase the cost of your components, as you increase quality, you're also going to, of course, increase cost of the final product that you buy from that vendor. Another thing is your servo size. Most servos are going to be standard sized, and the exact standard size specifications, there's no rule book that every servo manufacturer gets in the mail when they start to make a servo. Standard size servos is kind of a generalized term that's a catch-all that can mean servos about this size. So keep in mind the exact servo you're working with when you're designing a mount or using other stuff like that. And that can help you a long way when making sure your holes line up with the ears on your servos and stuff like that. You can also go smaller. There's lots of granularity in how small you can make your servo. This one is a Cr Servo by Hi-Tech. It's let's see if I can even read this. It's an HS55. So it's really, really small. It's got a smaller output spline. It's going to be a lot lower power output, but it weighs 9 grams. So if you have something where weight is really, really important, like a small scale RC airplane, it can be great. You can also get low profile servos, which are going to be a standard size servo that's a little shorter, generally. You can also get larger size servos. That is a great thing. I will start that giveaway right here soon. Today we're going to give away a set of goBILDA servos that will have one of each of our ratios, and that should be started now. The keyword for that is, let's see here, steel gears, all one word in the chat for your chance to win a set of those servos. So, and steel gears, the reason I chose that is because your goBILDA servos are all going to have steel gears. It's the kind of middle of the road option. It's going to be better than a metal gear. It's going to be better than a plastic gear. It is kind of funny to say steel gear is better than a metal gear when steel is definitely a metal, but most of the time when you're talking about a metal gear servo, you really mean a servo with a gear material you aren't particularly proud of. Something like a sintered aluminum or a brass. Steel is going to be like the one you really tout as a very, very strong option. And titanium is going to be your top of the line, really, really nice, low inertia, and really durable gear set. And even in a titanium gear servo, not every gear in the servo is titanium. It's going to have some mixed materials in there because in the early stages of a gear train, it won't see really any torque. And the advantages you get from having a really expensive, really nice gear train really taper off when you're talking about the first stages of a gearbox, where the mod of your gears might be 0.2, where they're just tiny teeth. Servo sizes, you can also go larger than standard size. High-tech 785 is a great example of the quarter scale servo. And an 805 BB is going to be a great example of a larger than quarter scale servo. Larger servos mean larger motors and generally more output power, but not always. A good example is a goBILDA servo is going to outperform a 785 in just power output. It's going to have more power and be an overall higher output system. The big advantage of a 785 is that they're multi-turn. So I can command this servo, instead of going 180 or 300 degrees, this servo will go 7.5 rotations. So you do lose some resolution, but you can run it on a lift, or you can run it on a servo gearbox with a gear reduction. This is a robotic arm with a multi-axis servo gearbox setup, where each axis has a 7-to-1 rotation just about. I think this early one might be a 9-to-1. But because of that multi-turn servo, you can still get one full rotation out of the output gear. A normal goBILDA servo, you would only get like 50 degrees or something like that. Less than 50 degrees if you put that in the same reduction. So that is a big advantage of the 785 and the 9382 high-tech's, like really top of the line servo. You get multiple rotations out of it. And that's kind of its own really separate class of servo that has some advantages and has some disadvantages, of course. Double reverse or double virtual 4-bar. Let's see. Double reverse virtual 4-bar. Okay. I actually have CAD one of those before. They're really cool. I really love double reverse virtual 4-bars. I have no idea if they're practical in actual like real robots. So the concept is that you have basically a normal chain bar where you have an input and an output, and these input and output they're always parallel. So as you shift through the movement, say your output would always say horizontal, or you can change the ratio to change the effective angle that it shifts to throughout the rotation. A virtual double reverse 4-bar would require a 1-to-2 to 2-to-1 from the input to the wrist, and then the wrist to the output, and then that would have a situation that would look like this. And you can get a really compact system to expand really, really long. I used this on a catathon I did back in the day. It's really cool. I think My memory of 971 in 2018, I feel like they were just a straight up multi-axis arm. 971 is always insane about their control. Their programmers are really out of their minds and can do some crazy stuff with just 5 motors on one arm, where your average person just looks at a virtual double reverse 4-bar and says, well, that's pretty easy to control. You can just run it to a position and your arm will get to a position. Where a multi-axis arm like this, you're not talking about moving one motor to get a certain amount of distance to get to a certain position. You're talking about moving potentially 4 motors to get to one position, and you can do that by moving this motor this many degrees and this motor this many degrees, or you can do that by moving this motor this many degrees and this motor this many degrees. So it becomes a really complex control algorithm that requires a lot of math and work through to really get implemented well. 971 is amazing because they do that, and they blow everyone away every year and are still massively competitive with that insanely complex system. A good example of that in FTC is Data Force last year. Their robot was overall super complex. It had a lot of different aspects, and they were still at least the second best team in the world. So you can be really, really complex and be really successful. 971, 6929, but I think that's more of the exception to the rule than the norm. Within FTC, generally a more simple concept with a lot of refinement can get further. But when you are really experienced, you've been doing FTC for years and years, you can start to do crazy things and be really good. And that is really exciting. I love seeing those teams who have been around for 5 or 6 years. Data Force is like 8 now. They were around for like 8 years, I think. And you have just a ton of experience under your belt, and you can start to do crazy things that are really, really fun. That last part didn't have a whole lot to do with servos, I guess, but FTC and all of that stuff. Servos can be a way to make your robot a lot more complex, but they can also be a way to make your robot simpler. You may find an application where you need to run a motor to a specific position over and over, and you don't need the full output power of a motor. That's where a servo is going to be great. Where I think a lot of FTC teams struggle with servos is where they use them to replace motors. And where you have an arm that really needs a motor, but you've budgeted all your motors somewhere else, and you grab 2 servos and say, this is good enough, right? Where that's really tough. We can always compare the input power between a motor and a servo. goBILDA servo at 6 volts is going to pull 3 amps. So you can take 6 times 3. It's going to pull in 18 amps. A yellow jacket is going to pull about 9.2 amps at 12 volts, which is 110 watts. So you can really see the difference in power between a servo, a pretty high power servo, and a yellow jacket, where they're really not comparable. And an application where you might use one, you would never think of using the other, because they are really pretty different worlds. Let's see here. Glitch just says, when you get your teacher off topic. Yeah, I love talking about 971 and 6929 are both just like mind-blowing, really, really amazing teams who I just love talking about. We should probably roll for our giveaway, pick our winner, and all of that stuff. So if you want to make sure to get that keyword Steel Gears in the chat and get your chance to win, make sure you're following and all that. And if you do end up winning, shoot us an email to marketing@gobilda.com and let us know your shipping info, your name, your address, all that stuff. Email address never hurts, and we'll get those sent out to you pretty fast. One thing a lot of teams ask me is, how much money do I need to spend on a good servo? And how long should I expect that servo to last? So, and that's always a tough question to answer, because you might want to run out and spend $180 on a 9382. Like, that's going to be a freaking awesome servo, but in most applications it can be wasted. And you can look at solving that problem in different ways. Where one team might solve that problem with a $200 multi-turn servo and a winch pulley, another team might solve it with a 180-degree servo and a linkage. There are always lots of different ways to solve problems, and sometimes those really expensive, really amazing servos can be the highest performance way to solve the problem. They can be the way the teams who win worlds solve that issue, but a lot of times that's not going to be the most effective for your average team who is thinking about spending $120 on 4 new motors as a big investment. They're looking at spending money on a strafer chassis as a big investment, and spending that much money on a servo that you might accidentally break is a really, really huge investment for something that probably won't pay off. When you're looking at upgrading a servo from, say, a goBILDA servo to a really high-end high-tech, make sure to keep in mind how much time it's going to save you in your cycle. If you think that faster servo will save you a quarter of a second, definitely make sure to look at other ways you can allocate your budget to save that quarter second. You may find something that's going to be more efficient and will save you that quarter second cheaper. And then later down the road, if you make worlds and you're really looking to get that extra quarter second, you can always go back. But buying the highest end servos is not always the answer. That's really the goal for our goBILDA servos lineup. We want to give that halfway point between an $11 servo and a $90 servo, where you can get pretty good performance and a lot of usability without breaking the bank and at a price point that most teams can afford, especially with the FTC discount. Jason E2212 asks, what are those two servos on the left, the red and black one? This is a high-tech HSB 9380TH, and to make sure, this is an HSB, not an HSR. So it's high-tech's kind of top-of-the-line, torquiest, brushless servo. It's really expensive, but it's a great example of a titanium gear brushless servo. This one right next to it is a D950 TH. It's also going to be a titanium gear, but it's going to be a coreless servo. Externally, these two servos look really similar. They have similar top cases, and they're both going to be high-tech servos. You're going to spend a lot more on the 9380, but you're going to put in a lot less power and get out a very similar amount of power. You may put in 7 amps in a D950, where an HSB 9382 is going to pull 2.5 amps, and you get out a pretty similar amount of power. That is how insane brushless motors are compared to coreless or brushed motors. They are way more efficient, and especially stall torque is not a very great metric for brushless motors because they don't get all the advantages of being a brushless motor. Where they really shine is when you're running throughout a rotation and you can get magnet alignment after alignment. So stall torque is not the place they really shine. Where brushless systems shine is the peak power output of 50% of their stall load. That's where they're really awesome. So we'll actually roll for our giveaway here. We'll close the entries and pick our winner. It looks like Diamond Goddess 14 is our winner. Make sure to shoot us an email, marketing@gobilda.com, and we will get you your servos out pretty fast here. That'll just be one of each of the ratios of goBILDA servo, and that should be really fun to get you started on a lot of those projects. Low-profile servos do look kind of funny, especially if you look at their gear trains. If you have a few extra minutes sometime, looking at low-profile servo gear trains is really cool. They do it in a very different way than a standard size servo does. An important thing to think about servos is make sure you're supporting the output shaft. There's not a whole lot of support on this, so adding a servo block or a gear system externally can help improve their longevity a ton. Let's see. Algebra Gamer 20, definitely, I totally get where you're coming from. Servos are tough and they can be a lot of money, and it's hard to spend it because they don't feel like they're amazing compared to motors and all that stuff, but small scale servos can be a good investment, and they should be able to last you a long time. Jason asks if you can get positional feedback from a Cr servo. There are a couple servos out there that let you do that. goBILDA servos don't have that functionality. A big reason that they don't is that the goBILDA servo only has feedback for 300 degrees of rotation. With the way potentiometers work, we don't have a ton of time, so I won't get into that today, but there is no way to make a full 360 degree potentiometer because you need some input and output for your system. So 300 degrees is generally the most you can get out of it, out of the more standard size. Stealth X051 says you can use an external encoder for sure. That's a great way. And a continuous rotation servo and an external encoder is a great way to get to a custom built multi-rotation servo option that can run your lift system or something like that. So those are all really great options, and they can help you a lot with your overall building of robots. If you have any more questions about servos, goBILDA stuff, anything, shoot us an email to tech@goBILDA.com. If you want to see us again, we'll be here every Friday at 5 Eastern. You can find us at www.goBILDA.tv, and it'll take you right here to Twitch. Thank you guys for tuning in today. It was really a lot of fun to talk about servos and be able to rant about a topic that I really love for a while. So thank you for tuning in. We'll see you next week.